Welcome to my video on understanding an IR thermometer readings and emissivity. First I want to look at the equipment I was using to take these measurements. I had a Kizen LaserPro LP300 IR infrared thermometer, using that to take my measurements with. And I did just a room temperature on a table, so everything was at the same temperature. And what I did in this video was I investigated how the emissivity and reflectivity of materials influence IR readings. So it's something you need to take into account when you're taking measurements. And so what I did was I measured with that thermometer styrofoam, aluminum foil, copper, wood, and then cardboard. So I measured those 5 materials at room temperature and saw how the readings slightly differed through the photometer. Okay, this is the actual readings that I took. First I did the wood, and you can see the red dot pointing to the wood itself, and that just tells you where to point. That tells you where you're taking a reading. The wood gave nice consistent readings. The top thermometer there is just the ambient air temperature. And then this is a piece of copper that I measured, but I got some fine sandpaper and polished it off so I get a good clean surface. More indicative of copper rather than the copper oxide. Took a piece of styrofoam, just packing material. It measured real close to ambient temperature. We'll find out about emissivity later. It's got a mid-range emissivity. And this was a piece of aluminum foil, and it gave not a very good reading at all, just because it's so reflective. It has a very low emissivity and a high reflectivity, and it gets all kinds of stray radiation that messes up your readings. So you'll get a wide variation in aluminum foil or anything reflective. And finally, I did a piece of cardboard, just a generic piece of cardboard. Got a piece of shipping material, and it's got a fairly high emissivity and low reflectivity, give pretty good readings. Here's my results. First of all, this is the ambient air. It kind of warmed up a little bit during the readings. Probably had to do with the heater coming on, but that was the average. And the piece of pine wood gave nice consistent readings, 71.1. The clean copper gave a little higher temperature reading, which we would expect. It has a lower emissivity, reflects more stray light, so it read a little higher temperature. The styrofoam, nice solid reading. And then the aluminum foil was much higher than the other readings, and that has to do with the very low emissivity of the aluminum and the high reflectivity. And you're getting all kinds of stray radiation in your detector. And the cardboard gave a nice smooth result. This graph shows the deviation of the measured temperature from the room temperature. Pine wood was a little bit below. The clean copper was a little bit above. Styrofoam about right on. And then the aluminum foil gave a much higher reading, about 6 degrees higher than what we would expect. And I'll talk a little bit more about why that is. And the cardboard was slightly lower. So everything but the aluminum foil would be considered a reasonable reading. Blackbody radiation and color temperature. So the idea of the infrared thermometer goes back to the idea of the blackbody radiation, which was first studied by Max Planck back in the 1920s, 30s, somewhere in that region. And it measures the temperature of an object based on the amount of light and what the wavelength of that light is that comes out. If you put a hot poker in the fire, it's going to start out at a dull red, then get red, orange, white, and then if it cools down, it goes back to that sequence again. So the temperature, as the temperature increases, the color of the light changes, and that's what the infrared thermometer does. It measures down light in the infrared region that we can't really see with our eye, down this region in here. So that's what it's going to be measuring in. So what is emissivity? You heard me use that term earlier. Emissivity, it measures how efficiently a surface emits infrared radiation compared to a perfect black body. The infrared photometer assumes a perfect black body with an emissivity of 0.95 on this particular model. So an emissivity for a perfect reflector like a mirror or a piece of shiny silver, it's going to be close to 0. doesn't emit a lot of radiation, it just reflects it. Now, a perfect emitter would be approaching a black body, a theoretical idea, and that's going to be like a piece of coal or a dark piece of metal. It mostly just emits radiation. It doesn't reflect anything. It absorbs and re-emits. So high emissivity materials emits most of its IR radiation. This is going to be like the wood and the cardboard gave good readings. Low emissivity, we're going to see, would be like the aluminum foil and the shiny copper. So typical values for the material we did in this experiment, wood and cardboard, it's in the upper end of the scale. It's close to Blackbody, 0.9 to 0.95. Styrofoam is somewhere in the middle. And then the cleaned copper or the aluminum foil has a low emissivity. And that's why we get the readings that are a little bit high, because it's reflecting other radiation into the detector. So why emissivity matters for infrared thermometers? It detects the infrared radiation and converts it to temperature. That's how it works. And so it assumes, in this case, you can buy other thermometers that have different emissivity, or you can adjust it even. This was a rather inexpensive one. I paid less than $20 for it. It assumed an emissivity of 0.95, nearly a perfect black body. And so as the emissivity of the material is different than that of a perfect black body, you get different readings. So if the true emissivity is lower, like in the case of the aluminum foil or the shiny copper, your temperature is overestimated. And so shiny materials reflect IR from surroundings, that could be from the window or even from myself. I emit infrared radiation just like every warm body does. So what we can look at this, the high emissivity materials like the wood, the cardboard, and the styrofoam closely match the ambient readings. And then the low emissivity materials like the shiny copper and the aluminum foil give a higher reading than you expect. And so the reflectivity and emissivity combined, they distort the results, something you need to take into account. And sources of error here would be the IR reflections from surrounding objects, the incorrect emissivity assumption of the material, they're not all at 0.95, and then the variation in distance and angle. I could have made this more accurate if I'd mounted the detector and had the same angle and same distance each time. I tried to maintain that as much as I could, but I'm sure there was some variation. And then the surface cleanliness and oxidation differences. That's why I cleaned the surface of the copper, to get the oxidation off. Now I could have improved my accuracy of this, and I may do a video in the future where I do this. I could have put some black tape, like black electrical tape, on each of the objects and measured that. That temperature would be the same and the emissivity would be around 0.95. And I could have mounted it and get the same reading each time, like the same angle, same distance. And I could have done it in a darkened room and stood further away from it where my body was not radiating heat, there wasn't stray light. So I could improve the measurement by doing a few basic things. So what we can conclude from this, IR thermometers rely on emitted infrared radiation, not direct contact temperature. Blackbody radiation and emissivity determine the apparent temperature reading. That's the two things it uses, the wavelength, the intensity, and then the assumed emissivity. Metal and shiny materials distort readings due to the low emissivity of the material. And understand these principles ensure accurate measurements. The more you understand about how these meters work, you can understand their differences and problems and get a more accurate reading. I want to thank you for watching. Hope you learned a little bit about IR thermometers.